Wonderful. Welcome, everybody. I think we're about to get started. So we're very fortunate today to host Professor Gordon Baym from the University of Illinois Urbana-Champaign. Gordon has a very long Wikipedia page listing his many accomplishments and prizes and successes. So I think most of you probably have read them already, so I won't try to list all of them, except to mention that, of course, Gordon has won just about every prize available for his amazing career over many decades, studying everything from nuclear physics to the inside of neutron stars. And we are really fortunate to have Gordon visiting us today. And I'm going to turn it over to Gordon because he's much more excited to listen to than I am. So, Gordon, thank you for coming. And please, the floor is yours.
Is the microphone working? Yeah. Great. Okay. It's great fun to be here. I've my first trip to Melbourne ever. I want to talk about neutron stars, and the last 15 years have been quite an amazing period in development of our understanding of neutron stars. I want to review some of the important things that have happened here. Here's a rough picture of a neutron star. There's a solid crust, good metal. As you go in maybe a kilometer or so, there's a core of neutrons, protons, and electrons. Interesting question: what's happening at much higher density, and perhaps a continuous transition to a quark-gluon plasma, or at least quark-gluon degrees of freedom begin to become important. Masses are on the order of 1 to twice the mass of the sun. Radii, 12, 13 kilometers. And in fact, they're really giant nuclei with baryon numbers of order 10 to the 57 particles. By the way, anybody know where the 57 comes from? Here, it's not a random number. It's the gravitational fine structure constant. Big G, Newton's G, that's the mass of the proton squared, divided by h bar c, is 10 to the minus 38. And then from 38 to 57, you multiply by 1.5. That's that number. Yeah. Okay. And the magnetic fields can be anywhere from 1,000,000 Gauss to up to magnetars magnetic field, perhaps 10 to 16 Gauss here. I won't get into any of the strong magnetic field physics. The surface gravity of neutron stars is gigantic. I mean, if you drop this, it falls at some rate. If you do the same on a neutron star, it'll fall 10 to the 11, 100 billion times faster. What that means is the surface gravity of a particle on attached to the surface is about 1/10 of its rest mass. So that's because if you try to remove a proton from the surface, it will cost about 100 MeV. Okay. So this is just a general picture of how the neutron stars fit into the general scheme of things. They're primarily made in gravitational collapse of massive stars and supernova, but there's another pathway that we've realized in the past 10 years, which is as a result of binary neutron star mergers, of which we have one clean example from 2017, that could also lead to a neutron star, a heavier neutron star. The matter is extremely dense, 5 to 10 times the density inside normal nuclei. And so if you take if you look inside a normal nucleus, like a species of uranium, the density of matter is about 0.16 particles per cubic Fermi. A Fermi is 10 to the minus 13 centimeters. And so this is extremely dense matter. What prevents neutron stars from collapsing is not white dwarfs are held up by electron degeneracy pressure, but what prevents neutron stars from collapsing is basically neutron degeneracy pressure, and perhaps the higher densities, the quark degeneracy pressure as well. And they occur all over the place now in interesting gas physical systems, ranging from pulsars, the first discovery, to binary neutron X-ray sources, soft gamma ray repeaters, magnetars, fast radio bursts, and so on. And they're also very interesting as being the only place where you really can study very high density matter. The where you consider cold high density matter and begin to learn some of the properties of quantum chromodynamics here. Okay. Let me give you a very brief history of neutron stars. The neutron was discovered in February 32 by Chadwick, and he sent a letter to Bohr, to Niels Bohr, suggesting a particle which had probably have a mass almost equal to that of the proton. And the letter is February 24th. A few days later, he's interviewed by the New York Times. Dr. Chadwick only smiled, however, when asked if his discovery had practical importance. I am afraid neutrons will not be of any use to anyone, he said. Basically, we'll never predict the future. And then the fact that it had a mass almost equal to the proton really bothered Chadwick. And this is 6 months later, he writes, the belief that the neutron is a new ultimate particle like an electron or proton was challenged today by Dr. Chadwick, the young discoverer of the elusive neutron last winter. People in 1932 had no idea that particles came in multiplets. And it was just too much to ask that there be another particle that looked exactly like an electron or proton bound together. They have just about the same mass. So it must have been electron proton bound together. Yeah. And people learned over the years. Okay. But the first real proposal of neutron stars was bought at Zwicky in 1933, where they followed up. This is Zwicky here, where they followed up with the paper on the. Oh yeah. So this is the original Zwicky proposal. This is the bulletin of the American Physical Society. With all reserve, we advance the view of the supernova and represent the transitions from ordinary stars into neutron stars, first mentioned, which in their final stage consist of extremely closely packed neutrons. Exactly right. But even more than that, what's quite amazing is this is again December 33 in January 34. Zwicky's interviewed by the Los Angeles Times, and he writes, correspond to little spheres 14 miles thick, which is precisely what we were measuring nowadays. How he did this, I have no idea. And considering that he's spending all this time discovering dark matter instead in the coma cluster. Yeah. Anyhow, then nothing very much happened with neutron stars. In 1939, Oppenheimer and Volkoff discussing what Tolman invented the Tolman-Oppenheimer-Volkoff equation, and they did the first calculation of neutron stars based on general relativity, where they assumed free neutrons. And what was interesting about this is they got a maximum mass of 7/10 of the solar mass. And the fact that we see neutron stars up to well over 2 solar masses tells you that interactions are playing a very important role here. Oppenheimer also at the same time invented the black hole, but never followed any of this up. Of course, a war came in intervened. By 1966, John Wheeler, his Wheeler, was very pessimistic we'd ever see anything about neutron stars. A cool superdense star is fainter than the 19th magnitude, and therefore hardly likely to be seen. The rapidity of cooling makes detection even more difficult. This is 1966. Then, a few months later, Jocelyn Bell discovers pulsars here. And these are the traces going beep, 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 beep. She was actually trying to discover quasar radiation here. And this is just a nice accident. And they were identified by Tommy Gold and also Franco Pacini as rotating neutron stars very, very, very shortly afterwards. So the standard picture, which I'm sure you're all familiar with, is you just have sort of a beam coming around. Every time the beam flashes past you, you see a pulse. Okay. Oh yeah, but notice here that the tracks are labeled LGM1, LGM3. LGM stands for Little Green Men. But she wrote it was highly unlikely that there would be 2 lots of little green men on opposite sides of the universe, both designed to signal at the same time to a rather inconspicuous star and a rather curious frequency. Yeah. Anyhow, so Jocelyn Bell discovered pulsars, from which her advisor, of course, got the Nobel. Tony Hewish got the Nobel Prize, and she She apparently wasn't even invited to the Nobel ceremony, but things changed. Okay, another green man. Now, let's switch to how we begin to understand neutron stars. Now, there are two approaches. Well, I've been in the game since the discovery of pulsars, basically, and what we try to do is come up with the best theoretical pictures of what matter look like. But in the past 15 years or so, there's been explosion of observational data, which has been really much more useful. Now, the problem with theory is you'd like to write down the equations of quantum chromodynamics, solve the axioms of neutron star structure, solve away, and come out with the answer. And you can't do this because quantum chromodynamics is very strongly interacting theory, and we have no way of solving the problem at finite baryon density. You could solve using what's called lattice gauge theory in the vacuum, where you have no net baryon number, but it's just going to be hot. That problem's solved. But if you just increase the density at zero temperature, the methods run into difficulty. It's something called the fermion sign problem, and you just don't get very much information. However, the observations have just really exploded in the past 15 years. So the picture, if you want to just model neutron stars based on pure thought, what you would calculate first is the energy density as a function of the baryon density here, and then you calculate the pressure by this simple derivative. Pressure the energy, the volume is the same equation, and then the Tolman-Oppenheimer-Volkoff equation, just the equation of hydrostatic balance over here. And if you cross out all the terms of 1 over c squared, it's just the things you teach the undergraduates that determines the structure of the atmosphere as a function of height and such. And then the mass is the integral from 0 out to the radius, 4 pi r squared dr times the mass density of r. And this looks deceptively simple, but full of general relativistic corrections, all of which cancel out to reduce the simple Newtonian result. And so here's some pictures of neutron stars by my colleague Vijay Pandit, Jeffrey Egerton, and Sid Akmal from years and years ago. So mass versus central density, and it's the first order differential equations. That means you pick a density in the center, integrate outwards, and then you construct the mass versus density. You get a curve like this, or depending on the equation state you pick, it can go to higher density here. And radii, this is radius versus mass, looks like this over here. So the reasonable best guess over here was sort of this curve that's just tangent to the green line over here and over here. And notice this gives a radius of something on the order of 10 kilometers. And we thought that was pretty nice. That we quite reasonable size. We have much better information at this stage. Here. Okay, I'll come back to these later. But I want to spend a little time discussing observations. Did the Simpsons come down to Australia? Yeah. Oops, okay. So what do we know? The observation. Detection of heavy neutron stars and pulsars. I mentioned gravitational waves from neutron star mergers, neutron star black hole mergers. These begin to explore masses, radii, equations, state, tidal deformabilities, and such. We know about production of heavy elements via the R process in these, the gold, silver, and so on. And through pursuing the LIGO-Virgo collaborations, and soon maybe cosmic explorer, the Einstein telescope, and LISA in space. Very important has been NISO, which I'll say in some detail, which is measuring mass and radii of neutron stars for a few pulsars. Something I won't dwell on are pulsar timing arrays, which are absolutely marvelous because neutron stars are once this curiosity, and now we're really using pulsars themselves to measure gravitational waves, which is an incredible development. And eventually, this will lead to things like a pulsar GPS system here for celestial navigation. And I won't talk about other things. Neutron star glitches, sudden speed ups. This is actually an Australian picture from 1969 of the veil the pulsar, so they slowing down, speeding up and slowing it down again, which gives you probes of possible states of superfluidity of neutrons or protons, and also make information about the crust. And I will talk about cooling of neutron stars, which gives you other information also. Yeah. Well, here's a picture of neutron star masses. This is 10 years old by now. What you see, first of all, the binary neutron stars all seem to be around 1.3, 1.4 solar masses. And people thought this was bad. This is correct. All neutron stars should have masses like 1.4 solar masses, because 1.4 happens to be the Chandrasekhar mass limit for white dwarfs. That's held up by electron degeneracy pressure. There's nothing, the Chandrasekhar limit has nothing whatsoever to do with neutron stars, but it's convenient coincidence. So people thought that was important, but it's not. Over the years, people discovered the pulsar mass increasing, and sort of in the past 7, 8 years, so there's three interesting heavy neutron stars which have white dwarf companions. And the white dwarfness of the companion is important because that means the dynamics of the companion, basically white dwarfs have no interest in the dynamics, and there's no interference with the measurement of the pulsar of the neutron star mass here. Okay, so these are the three interesting objects: the 16, 14, 20, 30. They're all off telephone numbers. Mass 1.9, 2.01, and the heaviest one is 2.08 solar masses here. Okay, this is just a more modern version of the same picture, but it's filled in by Jim Latimer. Okay, now what do you learn from masses? First thing, these pulsars, these are the masses of the year of discovery. You learn neutron matter is stiff. If you make this plot here of the mass versus central density, and soft equations of state will go to high central density, but never get very high in mass. So these are very soft equations of state going up to 1.6 solar masses. On the other hand, if you have a very stiff equation of state, it can rise up to a high mass, support a large mass, but it doesn't get to very high density. So any discovery you make of a mass tells you, let's say, if you discover mass where this green line is, all the equations of state down here cannot be right. They're too soft. They cannot explain that mass. So a single discovery, a single observation of a mass tells you immediately the equations of state must be stiff enough to support that mass. And so, well, at 2.0, 2.1 solar mass are up here, and so there's not much room up here for not too many equations of state begin to explain neutron stars here. And so that's been very important. The other interesting question is, can quarks in the interior, and I'll come back to this, can quarks in the interior by themselves support two solar masses? And the answer for many years, which I'm responsible for, unfortunately, was no, it can't, but that was wrong. Yeah. Okay. There are other masses of possible stars that may be very massive. This guy, Roger Romani's star, which has a mass of 2.35 plus or minus 0.17. The trouble with this is the companion, it's a black widow pulsar and sort of a helium, probably say helium star 0.032 solar masses. But the trouble is these have a lot of dynamics. They wiggle around. And so when you try to do timing measurements, the oscillations of the companion star misses it up completely. And so then they're not clean measurements at all. There's another one over here, this is 2.54, and this is Scott Ransom's object over here. And unfortunately, the companion has not been detected, and the people looking at the Webb telescope to learn about the mass, to learn about the companion here. So this may be a heavy neutron star, and then there's a Mercat observation, which is something in the range of 2.09 to 2.71. The companion of this pulsar is is a compact object in this range here. But again, one does not understand what that is, whether it's a neutron star or possibly a black hole. And another one is this X per se object here, we discovered by the Japanese, which is a binary pulsar, X-ray pulsar, with a beryllium companion. But again, the dynamics of the companion make this thing rather difficult to decipher firmly. But it's a mass of about 2.3 plus or minus 0.17. So there are future candidates for heavy stars. They'll be fun. I suppose most of you are very familiar with detection of gravitational radiation, so I won't have much to say about that. There was, of course, the spectacular event from August 2017, where one saw. How many people here actually saw this object? As you know, it's in the southern hemisphere, so you could have actually peered through a telescope to see it. Did anybody here actually see it? No. Okay. Anyhow, these two neutron stars emerging, giving rise to a kilonova. This merging of neutron stars, and this tries to be a rather interesting beast because it's this secret how to make heavy elements. I mean, here's a chart of the elements, and iron is sort of the heaviest element you can burn matter through it in stellar evolution. And how do you get all the elements beyond this over here? And people understood for many years what you did is you start with ordinary elements like iron, put them in a bath of neutrons, let nuclear physics click away, and out will come lots of heavy elements. But where do you get the neutrons? Well, supernova maybe, but the binary neutron star emergence are marvelous because you take these two bags of neutrons called neutron stars, merge them together. You got a big system of hot neutrons, iron, and just things go on. And the observations of the spectrum, which I won't get into at all, that I guess the only element that was firmly identified was strontium. But there's good reason to believe that one is making all these heavy elements, all the ones that look like this, through uranium and such, thorium. These are all made in binary neutron star mergers, which gives you a wonderful way to look at gold, a piece of gold. Every time you see a piece of gold, remember that those atoms were souvenirs of their days in neutron stars. Here, basically. Okay. There have been some neutron stars. There's this binary neutron star merger in September 25, but nothing very much happened with this because there were only limited detected saw, and there were no electromagnetic signals that could be identified with the event. Another interesting event was this 1908 14. I'm sorry, this was not 25. This 2019 April 25th. There's a black hole with a very light object that could be a neutron star or a black hole, and then there's some neutron star black hole binaries that list over here, and not really we haven't learned very much from this except from the initial 1708-17 event. But it's the next LIGO Virgo cover run 05, which is predicted to give something like 20 or more binary neutron star mergers per year. And then when we get to the Cosmic Explorer and Einstein telescope, then this can produce at least 100. And when you're at the level of one neutron star merger every 3 days, theorists are going to be very, very busy at that time. It's going to be great. Okay. This is one wonderful picture that's assembled at Northwestern. This shows various neutron stars. My one contribution to this picture was to get to put error bars on neutron stars. Otherwise, the original picture, look, we knew hundreds of neutrons, had firm measurements of hundreds of massive neutron stars, but we didn't. Yeah. This is a more modern picture, but it's pretty, but useless. Except some details in here. Okay, and this is the future LIGO Virgo timeline. We're just right here. The 04 run is over. 05, you folks probably know much more about when something's going to happen. maybe. Okay. And this is a very nice plot also. This is the cumulative detections in the various runs versus total running time. So things are going up at a rather rapid pace here. Yeah. Okay. Let me turn to NICER. NICER, which stands for, it's an acronym, Neutron Star Interior Composition Explorer. And it is basically a sort of refrigerator-sized box, that's sort of twice the size of this table that's been sitting on the space station since 2017 now, and it's been measuring. It's just been measures very good X-ray timing to 300 nanosecond accuracy, and spectroscopy from a tenth to 10 keV. And the aim is to measure neutron star masses and radii here. And so far, there's been two very interesting results, which I'll come back to. The very heavy, the first one was a 1.44 solar mass star with a radius of about 12.4 solar masses. And the other is this heaviest neutron star, 2.08, which has a radius of about 12.3. These two numbers are very interesting. They're the same. And you have to ask, how is that possible? Well, I'll come back to that. I do want to point out that how does NICER work? NICER works, it depends on the light bending by gravitational, but it's strong gravity. So if you have a star here, a light beam comes along, gets bent, and the observer is here. But what this means, if you look here, any light that originates behind the star can be bent into the field of view. So you can see behind the star from a little bit, depending upon how strong the gravity is over here. And so this is very nice. Sharon Morse's lovely movie that shows an ordinary star with gravity, a hot spot, and the hot spot is available. You can see it for only half the period. On the other hand, due to strong gravity, the hot spot is now behind the star because we get to still see it a little bit. And so this is an exaggeration showing you can see hot spot for 2 pi altogether. Now, an interesting question. NICER is measuring masses and radii separately. It's measuring an angle. An angle is dimensionless. How do you get a mass and radius separately? You could get the ratio of mass to radius by measuring an angle, but to get them separately, you need some other dimension coming into the system. And what this is rotation, the rotation rate of the stars. So all the data analysis really involves using strong the full curve metric to analyze the data. Okay, and these are the results here. This is the first one that was measured in 2019, mass about 1.44, and some recent measurements over here, but I tend to put more weight on the upper ones here. There's the 0740, this is the heavier one, which amassed someplace between 12.39 to 13, depending upon the assumptions you put, the amount of priors you put into the analysis. Such. Then there's I'll give you a copy of this. A few more objects over here. This one turns out very small, but the authors admit it's a quote a complex case, which means don't believe it yet. Okay, and then there's another one down here, but the lower ones here, these two shouldn't be taken too seriously yet. And there's one more pulsar in the pipeline here. Okay. Yeah. Okay. So this is the basic picture that if you plug this is mass versus radius here, and this was Cole Miller's analysis from University of Maryland and Urbana. What's very interesting here is that within the error bars, the light star and the heaviest star, seem to have basically the same radius. And that's a very difficult question. How can that be? The general rule, and I'll show you examples, is you take any equation of state, nuclear equation of state, the more mass you put on, the stronger its gravity, the smaller it becomes. I mean, it's like you lie down on a pillow. If your head's very light, the pillow condenses a little bit. If your head is heavy, the pillow condenses a lot. This seems to indicate that neutron stars are magic pillows. You lie so softly, goes down a certain amount. You put a heavy head on, goes down still about the same amount. There's some internal feedback mechanism is happening there. And the question is what is going on? And I think it's really pointing the possible existence of role of quark degrees of freedom of becoming excited and could entering the equation of state. Okay. This is very nice picture of Sanjay Reddy showing how that if you have very soft equations of state, the squishy things, you get mass versus radius will go this way, and so the more mass you put on, the smaller becomes the radius. The fact it's not doing that at all is eliminating the possibilities of soft squishy equations of state, and in fact eliminating possibilities of equations of state even with sharp frictional phase transitions in here. Okay. This was short. My picture. I showed this picture earlier. It's a little fuzzy. But again, mass versus radius based on nuclear equations. What you should see here is that the lines all slope this way, which is saying that the more mass you put in the star, the smaller becomes the radius. All nuclear equations say have that property. You can't write. If you look carefully in literature, you will find equations of state that assume we have nucleons at effective masses, which is 1/100th of the regular nuclear mass. And if you put enough crazy assumptions, you can get anything you want. But ones based on unknown physics do not all have this property that the radius will always decrease with mass here. So something else, it appears from LIGO data, is telling us that something else is going on. Okay. So this is the same picture again here. So the basic picture from my NICER is I think that something is happening in the equation state. Matter is getting stiffer as you begin, as you compress the material. My old postdoc Toro Kojo, who's at KEK, had a very, very simple picture of this. Is suppose you draw a simple distribution, like if you're teaching elementary statistical mechanics class, number of particles versus momentum. Things that would look like a Fermi distribution would look like this. And do this for the quarks in matter. At low density, there's very, very, very few quarks per available state. As you increase the density, however, the states fill up. Finally, at the low momentum, the states are filled with one quark per possible state. Because quarks are fermions, you can't add more. As you make the matter denser, what has to happen is that instead of having a higher number, which Pauli doesn't allow, you begin to fill higher momentum states, and that means you have more higher momentum particles in the system, which gives you more resistance here. And so the basic picture, I think, is that what NICER, I hope, is telling us is that as you squeeze the system together, the quark degrees of freedom are becoming important and pushing back here. Now, I'm not saying that the matter has dissolved into a liquid of quarks. This could be taking place well within the nuclei themselves. We don't know. We don't have the machinery yet to figure it out. But it's not saying that you have liquid quark matter. Yeah. Okay. So let me spend just a few moments to talk about quarks within dense matter. Quarks have been very popular everywhere. Certainly in the early stages of the Big Bang, up to the first microsecond, matter was dominated completely by quarks, and then nucleons hadrons begin to form, and eventually nucleons begin to form. At the relativistic heavy ion collider in Brookhaven, RHIC, and then the LHC, has been making quark matter, but hot quark matter. You take two nuclei, smash them together, and these look flat because of Lorentz time dilation, not Lorentz contraction. The spheres coming at each other, but they've got disks. They come at each other, they pass through each other, and what leave behind in between a very hot state of vacuum here. So we've learned a lot about hot quark matter. The trouble with all these experiments is they haven't begun to tell us what cold quark matter looks like inside neutron stars. Here. Okay. Yeah. So what does matter look like? The first phase diagram to try and guess what things might be was due to Cabibbo and Parisi. This is the density of baryons and temperature, and they said, well, there's two regions. This confined matter, like inside ordinary matter in the room, and very hot or very dense matter would be deconfined. The quarks would run around freely. This picture's got refined over the years. I wrote down this picture many years ago. But not knowing that Cabibbo and Parisi plotted temperature vertically and density horizontally, showing that ordinary nuclear solid state physics all takes place in this pixel down here. Nuclear physics takes place over here. But if you go to hotter regions, hotter or denser regions, you'll come into a deconfined region where the quarks and gluons are free to run around. Here, this picture has gotten refined over the years, and here is a oops. Yeah, more modern picture over here, and some of the features have been added. At very high densities over here, the matter becomes what is called the color superconductor, just like ordinary pairing in laboratory superconductors, only involving the quarks rather than electrons. Here, what's interesting about this is that this is the old Cabibbo-Parisi line, and it was realized by Ashikawa Yazaki that there's a crossover here, and that there would therefore be a critical point over here. So there's a line of first order phase transitions and then a crossover. And there have been recent Monte Carlo calculations, actually they're 10 years old by now, which show this region looking along the temperature axis. And as you go up, as temperature increases, pressure, this is entropy, nothing interesting happens. Everything goes smoothly across there. And what it's telling you, what you learn from these calculations, is that as you go up in temperature, there's a smooth crossover. This raises a number of serious conceptual issues. I hope I've convinced you now that matter comes in two phases. There's confined matter down here, where all the quarks are bound together. Out here, quarks are free to run around. If there's a crossover here, it means these regions are joined together. So if you start up here, you bring matter down to here, and does that mean if quarks are free to run around up here, they're actually free to run around in the room? If you look here at this quark, the answer is no. We're not allowed their quarks to run around freely in the room, and that means we're not really allowed their quarks running around freely up here. So this is a rather oversimplification of what's happening over here. What's really happening is that as you make a larger volume, like a nuclear collision, the quarks are free to run around the entire region of the volume. They're not allowed to run around outside the accelerator and other places. Okay. Okay, so that's our basic understanding. And so this is what I think is a reasonable picture of what the phase diagram looks like of temperature versus this is the chemical potential or density, is that hadronic phases here, there's a quark-gluon plasma over here, that may or may not be a critical point. The reason for a critical point is that this all started with a curve that blocked things into two regions over here. And then you learn it's not really divided into two regions. And the existence of this critical point, the thought that there is a critical point here is a remnant of this old picture over here. it's an important remnant because there's been a good study at Brookhaven and at the LHC to look for this the existence of this one in heavy ion collisions in experiment, and nobody's really found anything yet. But here, okay. What is interesting is different when you go down to very low density over here. The symmetry group changes, but the matter here becomes a superconductor with the U1 symmetries are broke. U1 baryon symmetry is broken, and so this region up here definitely distinct from the region down here. But this structure is very familiar. If you remember water, if you were to do a phase drawing of water, pressure versus temperature at 374 Kelvin, here there's a critical point. At that point, you can go from water to steam around this critical point without a phase transition. That's exactly what see. If there is such a line over here, it's just a line of first order phase transitions, like in water over here. So that means that this quark-gluon plasma is continuously joined with hadronic phase over here. Good microscopic pictures of what's happening are lacking. Okay, I just want to point out that heavy ion collisions have been very good at studying this region with no results so far. There is under construction at Brookhaven the electron ion collider. Don't ask me when it will be finished because nobody can predict anything now. But it's in the old Brookhaven tunnel where you have two heavy ion beams going around. There's one heavy ion beam and an electron beam going around, and they're smashing into each other here. And that would enable you to learn things of what's going on along the density axis here, over here. Okay. All right. So let me turn this question up. But can one have quark-chromatic cores inside neutron stars? Now, in the old days, I wrote down this picture here. How do you do this? If you're a good thermodynamicist, you have two possible phases. You write down a diagram showing down here this energy per particle versus density. The red curve is hadronic matter. Whoops. This thing it has its own opinions. The red curve shows hadronic matter, and they say, well, there's a quark matter, and quark matter at higher density, maybe at higher density has lower energy than the hadronic matter. So the blue curve is lower in energy than the red curve. And so therefore at high density, the blue curve is favored, the low density, the red curve is favored. But if you're a good thermodynamicist, you learn, you draw a tangent construction, the maximum tangent construction. And so you draw a curve that's bitangent to both these curves. And then what happens, you jump from here all the way up to here. You never live in here. So the matter will go from here, jump to here. So what that means is that you can get the very high density, but there's a very high density over here. And density with maybe 10 times nuclear matter density, you would not reach a synordinate neutron stars. So this picture, I think, certainly set back my thinking, even though I thought it myself, for a long time. There's several things wrong with this picture over here. One, it assumes that at high density, you have a choice, two possibilities. I'll go back to that. That you can have a high density phase of uniform matter or density phase of nucleons. Even though nucleons are big things, you can't squeeze it together. That's what's wrong. And the second is, notice that the only curves you will allow at high density, only blue curves you will allow at high density are ones that are below the hadronic. If you have a blue curve up here, you say that's not possible because it's above, it's too energetic. You must throw that out. You can't accept that. And so the problem is that you eliminate all stiff equations of state with quarks. So this is not the right picture. Okay. Rather, as I come back to this, it's really just basically one curve along here. I just want to back up a little bit and say, among other things we've learned recently, is what is called chiral effective field theory, which is basically trying to understand the properties of matter at nuclear matter density and above, just in terms of not deducing interactions of experiment, but looking at the basic processes in terms of the momentum transfer. So, for example, two nucleon force, you get a sort of a low energy transfer momentum between two nucleons, higher order terms than that, or three nucleon forces, and more complicated processes. Well, there's armies of people working on this now, quite successfully. The only problem is this shows the equation energy per particle versus density, which is, you need to know, this is nuclear matter density is here. Density inside of nuclei. And by this point, the error bars begin to get fairly large. At twice nuclear matter density, they're enormous. And so you can't believe that at very high density. But I think one of the things we've learned from this analysis here is that nuclear matter is somewhat stiffer, harder to compress than the old pictures we had in terms of equations of state derived from nuclear forces. And what that means is that neutron stars, because the matter is stiffer, neutron stars have a somewhat larger radius here. Okay. But then you ask yourself, does this whole picture make sense? Should we really be trying to understand force matter in terms of the interactions between separate nucleons? And nuclear matter density inside nuclear, it's fine. But then suppose you look at higher densities, several things, the problems that develop. One is that the sound speed becomes greater than the speed of light. And that's always terrible. That's when your grandfather sent a telegram to your father saying, don't have children, or various paradoxes like that. And then there's 3-body, 4-body forces. These grow with the number of particles here. The chiral effect of field theory breaks down. And then you raise the question, can you describe the matter in terms of few body potentials? Because these are more dynamical degrees of freedom. And can you even describe system in terms of the asymptotic laboratory particles, neutrons, protons, and stuff, or do other degrees of freedom come in? And there's several examples I'd like. One is, suppose we knew everything there was to know about atomic niobium scattering. So you sit in an atomic lab, and you in the basement somewhere, and you say, those scattering niobium atoms. Would you, and you get complete set of data, would you be able to predict that niobium metal is a superconductor on the base? And the answer is no. You can't, because other degrees of freedom begin to come in. In the case of niobium atomic scattering, it's electronic degrees of freedom that eventually take over. And the same thing here with you may know everything that's going on with nucleon scattering, but that's not telling you what the internal degrees of freedom of nucleon. Another example is take eggs. Suppose you knew everything about egg scattering. You do very, very low energy experiments. Be careful not to break them. Okay. And you know the complete hydrodynamics of egg scattering. Would you be able to predict that higher density, the system looks like this yellow stuff over here? Broken egg yolks. The answer is no. It's new degrees of freedom are coming in here. But you're supposed to say, but look, this is a very nice looking picture. This is almost right. It gives masses of the right range to solar masses, radii 11 instead of 12. So nothing wrong with it. It's a perfectly nice theory. But I'd like to emphasize the fact that it works does not make it right. And a very simple example of this, which comes from the theory of advanced arithmetic, which is this theory only a few of us know about. It's called canceling the sixes. You write down 16 over 64, cancel the sixes, you get a quarter. It's good. 19 over 95, cancel the nines, you get the right answer. But do 18 over 85, approximately a fifth. It's not completely accurate. It's a good first description of how to do arithmetic. And you can extend this to higher dimensions as well. I mean, 163 over 226 cancels 3.5. The fact that it's correct, the fact that it works does not make it correct. And the same thing with simple pictures of neutron stars in terms of nucleons and such. you have to understand the physics of high density, and does it make sense here? Okay. So let me just briefly say how we went about constructing this high density equations of state. This is work done with Tetsuo Suda and Toro Kojo in Tokyo. The point is, well, two things. If you want to construct an equation, say pressure versus chemical potential are by far the best variables to use. And what you know is what's going on at low density of a nuclear equation of state, at high density of a quark equation of state, and it's very highly constrained. You're not allowed to have the second derivative must be positive, otherwise the compressibility of the matter turns negative. So you can't have an inflection point in the equation of state. It has to be always continuously rising. It can have a discontinuous derivative, but it's got to be continuous. Well, what I'm showing you is just with a. I'm not going to get into any of the dynamical details, but I'm going to show you just two parameters. One is assuming a short-range quark repulsion and a pairing interaction, which is producing pairing like in ordinary superconductors.
Oh, so you're just saying that five. Sorry,
No.
that was meant to be roughly 5 minutes.
That's perfect. Thank you. So the minimum model, you say, well, take no interaction. You get a curve looks like this, and this is very soft. And if you calculate this, you find you don't get a high mass neutron star. So you got to make the matter stiffer. You can make the matter stiffer by putting in a short range repulsion between the quarks. And there's good theoretical reasons for doing this. It's not a random act. What happens, however, is the pushing the equation state out here. And now you see what you have is an inflection. Inflection points are not allowed. So this is not consistent. The inflection point. And so you can repair that by putting in a pairing interaction that says the quarks want to form pairs of quarks want to be together. The short range correlations that encourage having pairs of opposite spin, like in superconductors here. And then what you find is very nice. This curve over here shifts from over here, where you could not get a joint, to something that has a rather pretty joint over here. And so this way you could get a first picture of a consistent equation of state to explain heavy neutron stars, and still go from nucleons to quarks. This practically has a lot of pairing. It's nice. We like pairing because we know that even if quarks are high density and free to run around, at lower density they want to come together. They want to join together. Actually, it's triplets to form neutrons and protons and such. And a simple pathway is to form pairs, and the pairs pick up another quark to form triplets. Pictures that have not worked out completely. Okay. And so I just want to show some of the results and then I'll stop. These are what I'm showing here are just ranges of these pairing parameters here, and the strength of parameters, and this is basic picture also, is that when we look at the mass versus radius, we end up with a family curve looking like this. And this is very nice because these are the central densities, 2.1 times nuclear magnetic density, 3.5, etc. But what you see here is as you increase the mass, the radius is staying roughly constant. And that is what's seen by NICER here, which is very, very reassuring here. If you try the same thing with nucleon equations of state, it doesn't work. Well, okay. There have been these Bayesian analyses that look at all the possible equations of state in the universe, and done by primarily the Finnish group. Alexei Kurko is one of the members, and we got him to plot our equation of state, the black curve, on his results. It really runs right along the middle, very, very nicely over here. Actually, down here, it's wrong because he plotted the wrong equation of state down here. but that's a separate problem. But it's our equation is really doing very well. Then there's all kinds of monkey business at higher density, but that's not playing a role here. Okay, so let me see that. So let me just summarize here, which is, I want to say NICER has really provided the first empirical tests of theories of nuclear matter, which is quite amazing. And predicting neutron stars 12, 13 kilometers in some, revealing neutron stars at 12 to 13 kilometers of radius. It's shown the what looks to be suggesting equality of 1.4 and 2.1 solar mass stars, and further NICER measurements are in process, with analysis, NICER is sort of broken for a while at least. And so we will, over the course of the next several years, learn more about equation of state from NICER here. And just for challenges for the future, what one has to theoretically is build a consistent picture of matter above nuclear matter density from both the gravitational radiation data and NICER as well. But you need microscopic pictures of transition. It's a difficult problem to go from nucleons with nuclear big degrees of freedom, higher density, to quark degrees of freedom. It's the range in between where everything's happening. We don't really have good fundamental tools for describing that region. We don't have fundamental tools even ordinary condensed matter physics, how to go from sodium gas to sodium metal. It's describing what happens in between here. And I want to emphasize it's not good. You will see hundreds of papers that contain pressure versus density equations of state that fit the data. Anybody can draw a curve on a piece of paper. You can draw thousands of curves on paper. What you need to do in this game is understand what is the microscopic physics that's giving rise to that equation of state. That I think is the important challenge. And there are many other questions we don't understand, but I think over time we'll certainly do much better. So that point is said. Thank you.
Thank you very much, Gordon. I realize some people have to run, but for those of you who don't mind spending a few minutes, I think we have some time for questions. So Sharon, I think you were first. Actually, I'll walk around with the microphone for the people on Zoom.
Okay,
please.
You heard the you asked the question, if we know how two niobium atoms scatter together, can we ever predict superconductivity?
say it again.
So you asked the question.
Niobium.
Yeah, which I thought was a wonderful question. But let me put that back at you. In the core of the star, when we have all of these quarks, do we actually, and this is not a state of matter that we can easily create in the laboratory, right? So can we understand the multi-body quantum physics of this quark-gluon plasma that could have an impact on, the properties of the neutron star, or is it just enough to understand the microphysics?
Yes, can we? Is there a lot of time scale of the next 10 years? Or
no, I mean, can we actually hope to understand, the equation of state of the neutron star without understanding
we
this?
need our techniques to be able to calculate for quantum chromodynamics from first principles. And this fermion sign problem, which is the Metropolis algorithm for doing Monte Carlo, predicts the parts of probability and configuration. You do it for very dense matter, and it's giving you negative probabilities. And you don't understand what's going on there. It just fails. And so people are really trying to discover techniques for solving these problems, but it's down the road. And you can't do perturbation theory because it's a very strongly interactive system at the same time. So you do what you can. This is what we can.
I see.
Yeah, I fully agree with Sharon. That was a wonderful talk. So, I mean, the question is different. So, based on these this reasoning, so if you assemble a neutron star in different ways, for example, make a massive neutron star by merging two small neutron stars, or by taking the intermediate mass and slowly adding up some mass, do you expect them to have the same structure?
Expect
them to have the same structure in the end if they arrive the same mass?
Yeah, because there's a lot of time for the microscopic processes to take place, except in the crust. The outer regions you have, if you have accretion, for example, various elements accreted, and it takes a while to burn, pick the nuclear burning of material in the crust. But generally, in the interior, I think there's only one equation to see. Yeah.
Okay, can I ask another question quickly? So, well, I mean, okay, so you said it and heard it well also in regards to, Nobel Prize and everything. So, I mean, that, neutron mergers can produce, gold and all the things.
Yeah.
That's great. But I mean, it's clear that it's produced near the neutron stars. And then, like uranium, gold, and things are found on Earth in sort of like clumpy structures. I mean, in the sense that it's not like dispersed evenly throughout the planet. It's more like it's found in places like there is like some mine where they have a big presence of that. My question is, how does it happen that neutron stars produce that eject in all directions, and it lands up in these clumpy things? So
It's a very good question. I have no idea what the answer is. I mean, how come the gold ends up in a particular shop down the road that says gold rather than it's uniform in every shop in the street? Yeah, I have no idea. But it's good.
thank you.
Geology is interesting though.
Well, there must be some way because it also has to come to Earth first, right?
Yeah.
Okay, thank you. Sorry.
But there's so much to learn. It's great.
Time for more questions? Nisha?
Thank you, and very nice talk. Bit of a naive question maybe, but I was wondering, are there any like a good physical process to produce like subsolar mass neutron stars?
Subsolar mass? Oh, that's a wonderful question. We worry about that with no answers. The standard mechanism will produce neutron stars from 1.2 solar mass on up in supernova. Suppose LIGO turns up with a small neutron star. First of all, you have to tell us it's a neutron star, not a black hole, but that's an important issue. How could you make them? I don't have any honest answer. But like answers.
Sure.
Sorry, just a quick follow-up for those of us who don't know this well. What is the challenge in conventional theory with producing subsolar mass stars? Like, what's the challenge?
How do you do? Why does it happen? I mean, the basic the supernova picture you form core, which tends to be roughly 1.4 solar masses, and then
I see.
so then you get collapse and you lose some matter of shock ejection and such.
I see. So it's a problem with astrophysics.
Yeah.
Yes.
So I mean, the standard supernova route probably doesn't work, but there are perhaps other.
Oh, Paul, did you have a question?
Thanks for a great talk. That was really
Okay.
really interesting. So I'm an observer of gravitational waves, sometimes of other things. As an observer, what do you want? What's going to give you the most information to solve the problem of understanding the equation of state from a fundamental physics?
Gravitationally,
Sure.
certainly data at much higher frequency. I mean, the trouble is when you get to 500 hertz, you're learning all about the matter before the stars even begin to touch. And you get a little bit about the squishiness, but that's all in the outer layers. So you like some days you get to much higher frequency, be able to explore the frequency response to the interior matter.